Hey guys, this is Mozzie from Organic Chemistry 2 with Dr. Frazier. I just wanted to go over a couple of points that I feel like I wasn't clear on today in the presentation that I did. So here we go. One of the points that I wasn't clear on is what differentiates the different palladium catalyzed couplings from each other. So I went and took a look at all the presentations that have been done so far in the semester, not including the ones that are going to be in the future, and I thought I'll point out what the differences are. So the first one is going to be the hex coupling, which is going to be between an alkene and an aryl halide. And we can see the example here using a palladium catalyst. I didn't draw the ligands. We can attach these two carbons together. The next one is going to be the Sono-Gashira reaction coupling, which is going to be between a terminal alkyne and an aryl or vinyl halide. Now what's important about this reaction is that it uses a copper iodide as a co-catalyst, which introduces a second cycle into the reaction. The next one is going to be the Buchwald-Hartwig amination, which was discussed today, and it's going to be between an aryl halide and an amine. Here again, we use a palladium catalyst in a basic solution, and the result is the attachment of the carbon to the nitrogen. Now this is not a carbon-carbon bond, but since it was catalyzed by palladium, I thought I should include it in here. The next one is the Still reaction, which is between organohalides and organotin compounds. Now, as we're going to see a little later, in the second metal here is what defines this reaction. In this case is tin. In the case of Negishi, which I discussed today, is the zinc. So using a palladium catalyst, again, we are able to attach the two R groups together through a carbon-carbon bond. And finally, we're going to look at Negishi coupling, which is between an organohalide and an organozinc compound. And here's the shorthand of the reaction, and we're going to go and look at the complete mechanism together. So how this mechanism starts is initially we're going to have the palladium in the form of the ligand that we're going to introduce to the solution. And it usually has these two chlorines, which are good leaving groups, and using Dival, we're going to remove them, bringing the oxidation state of palladium from 2 to 0. So now that we have the palladium ready to act as a catalyst, we can introduce our alkyl halide. After the alkyl halide, the options in the R group are alkenyls, aryls, allyls, alkynyls, and propargyls. So through oxidative addition, which we discussed in the presentation, we are able to attach the R group as a ligand to the palladium, and this is going to be our intermediate before we enter the transmetallation process. In the transmetallation process, the organozinc that we actually create most often using Rake's reaction, it's called a Rake zinc, is going to enter the reaction. In this case, I put the mechanism by which the Rake zinc is produced. It's very similar actually to the Grignard reaction. This is going to be what's going to enter the solution. Unfortunately, I didn't include the halide during my presentation. I think that made some confusions. Now the R group that we're able to attach to this zinc Br group are going to be alkenyls, aryls, and alkyls. So through transmetallation, we're going to have both our R groups loaded out on our PD catalyst. and this is where the final reductive elimination takes place and gives our final product, which is going to be the two R groups attached together through a carbon-carbon bond, and the palladium going back to its zero oxidation state to start another cycle of reaction. Thank you.